So welcome once again to our online tutorials on mathematics. So today we're going to be going to a step further to learn about the concept of differentiation. Now, for emphasis sake, differentiation, you can check our previous video to see how to differentiate using the constant and the table of differentiation which we have. But for instance, if you have a curve, if you have a graph, if this is the y-axis and this is the x-axis, and let's say you have a line, you can take the slope of this line, which we usually call the slope of this graph, which we normally call the gradient, as a change from this particular point of x to this other particular point of x, which we normally call change in y upon change in x. So when you trace this down, you get a point of x here, let's say x1, and you trace this down, you get another point, let's say x2. Similarly, this point, if you trace it to the y-axis, this is y1, and also if you trace this point, it is y2, of course. So you can either see it as change in y upon changing, this is delta, or you see it as change in y upon change in x. So usually this is y1 and y2 minus y1, right, upon x2 minus what? x1. With this, you can get the slope, which we normally represent as m. Then in a straight line, if this is a straight line, and this straight line is usually governed by the function y is equal to mx plus c, where c is the y-intercept, which we have established that. We have established that before now. This is the y-intercept, then this is the slope, right? So this is called the slope, or you can call it the gradient. Now, this is practically simple, and we can do that from the previous video. As you can see, we have dealt with so many applications. Now, simply today, we are going to be talking about it using the concept of the first principle. First principle. Now, without wasting your time, the first principle, you can state that for a function f of x, right? If I want to differentiate f of x, I'm going to get f prime of x. And the definition, we are going to be using the concept of the limit which you have known. So is the limit as h tends to 0, then you have f of x plus h minus f of x, then upon h, right? I can also define it in terms of change in x. What is h? H is just this change in x. Change in x. This is it. So the same thing, this is your h. This is h. So I can also define this in terms of delta x as f prime of x is going to be the limit as change in x tends to 0, and f of x evaluated at a step further minus f of x, right? Then upon h. Fantastic. Now, for example, we all know that if we have a function y is equal to, let's say, x squared, right? If we differentiate y, we are going to get 2x, right? Because from our general formula, we have, if we have a function a is equal to n x raised to power n, right? If I'm going to differentiate this function, I'm going to get n a multiplied by n minus 1. And similarly, that's how we got this. Because of 2, multiply 2 by the entire function, we got 2. Then we have 2 minus 1, which we got x. Now, the concept of the first principle can still be applied to functions like this. So, without wasting your time, let's go to the application of this particular function. So here, instead of using h over here, I can use delta delta x, right? So this can be x plus delta x upon delta x. So I can use any of this definition for my solution of first principle. So for instance, if I want to differentiate f of x is equal to x squared using the first principle, then f prime of x is equal to the limit as h tends to 0 of the function uh, x plus h all squared minus f of x. F of x is going to be x squared, then this is upon h. Now, can I pass the limit here? No, because of the h that is here. If I pass h going to 0, if I evaluate the limit over here, I'm going to get 0 in the denominator, which we don't want. So basically what we're going to do right here is to expand this. I'm going to get 2 of this particular function x plus h, then minus x squared upon h. Now I can use the Pascal triangle. I can use the binomial expansion. I can just expand this as a quadratic function. I'm going to get the same thing, right? So the limit still stands. Then here, I'm going to have the limit as h tends to 0. If I should multiply this bracket, I'm going to have x squared plus 2xh plus h squared, because x squared, this is x squared, this multiplied by this is xh, this multiplied by this is another xh. Then that's why I'm getting 2xh, then h multiplied by h is h squared, right? And this is going to be upon h. So I'm done with this, then minus this guy. So I have minus x squared. Extend it. So x squared and x squared are going to cancel out. So I'm going to be left with 2xh. Let me write it over here. 2xh plus h squared plus h squared. This is upon h, right? I can factor out h out. So I have h into 2x plus, what is it called? This is h. But remember here, I have not taken the limit. So my limit is also here. So here I still have the limit as what? As h tends to 0. I have not taken the limit over here to I have my limit. H is going to 0. So I have this upon h. So this and this can cancel out. I'm left with 2x plus h. Now I can pass the limit since I don't have h in the denominator. So this is going to give me 2x plus 0 since h is going to 0. So simply I'm going to be left with 2x. You see, this corresponds with our solution here, right? So this is how to solve using the first principle. Fantastic. So we are going to be going to another example over here. Let me clear all these drawings. So we have another example over here. So let's try to solve when you have, let's say you have exponential x, right? Exponential x. If f of x is equal to exponential x, can you solve it using the theorem, the principle? Can you use it? If you can, if you have f of x is equal to, let's say, sine x, can you solve it using the first principle? And lastly, what you're going to be solving, if you have f of x is equal to 1 all over x, can you use the first principle to solve them? So I'll try to be fast. So now let's start with this particular, the last one, since it looked like what we have just done. So we have f prime of x is going to be the limit as h tends to 0, right? Of what? Of this particular function. Remember our function, our f prime of x is going to be the limit as either change of x or h goes to 0 is the same thing of the function evaluated at a step further, right, minus our initial function upon h, right? So this is very simple. So what we're going to evaluate right now is going to be this function at a step further. So evaluating that function, we're going to have 1 upon x plus h. Whenever I see x, I will replace it with x plus h. That's what this means, right? Then minus our function, which is 1 over x. Then this is all over h. Now, you see, your ability to evaluate this is very, very clear, right? So what are we going to do next? I can't pass the limit, obviously, from here. So all I'm going to do right now is try to evaluate the numerator so that h can cancel out. So by so doing, I'm going to take the LCM over here. For the numerator is going to be x into x plus h, right? So x plus h into this denominator, I'm going to get x. So here I'm going to have x minus. Now when x goes into the denominator, I'm going to get x over here plus h, right? Fantastic. So I've been able to put these fractions together. Then this is all over h. But remember, I'm still going to take this limit as h tends to what? 0. Fantastic. So the next step over here is going to be what? What's going to be the next step? I'm going to clear this fraction. So the limit as h tends to 0, opening this bracket over here, I'm going to get x minus h minus h, right? Because this multiplication is opening everything. Then I have upon, here we have x into x plus h. Then the last guy is h over here. So x minus x is gone. I'm left with minus h. So let's continue over here. The limit as h tends to 0 of what? What do we have? We have minus h, right? So we have upon x into x plus h. Now, instead of this long division, I can turn it to division over here upon h. It's the same thing. This is the division. This is also a division. So I can similarly go further to change this particular division to multiplication. And if I do that, this particular side of this particular expression is going to be flipped, right? So I have x into x plus h, right? So instead of division, I want to turn it to multiplication. So I'm going to have 1 upon h. This now turns to the inverse, right? Because I changed this sign. So similarly, h here can go with h over here, right? So what I'm left with, let's multiply them together. Here, minus 1 multiplied by 1. So I have what I have over here is going to be minus 1 upon, this is 1, so we have x into x plus h, right? So I can take the limit over here now. So if I pass this limit, I'm going to have minus 1 upon x into x plus 0, right? So I'm going to be having minus 1 upon this multiplied by this is going to give me x squared. And this become our solution for this particular guy. Fantastic. So before we go further, I would like to give us some particular standard for differentiation using the first principle. Now, one standard we're going to be using this standard to continue our solution, which I may prove them as time goes on this particular channel. So you have to just subscribe. Please subscribe and share so that you can get all the proof. Now, if you have exponential h minus 1 upon h, this is going to be 1. Remember, this is just change. So if I define this as the limit of change in x goes to 0, exponential. What we have here is change in x minus 1 upon change in x. This is equal to 1. So please remember, we are going to be using some other standard. Let me give you two more. If I have the limit as h tends to 0, change in x, right, of cos h minus 1 upon h, this is going to be 0. But if I have the limit, right, as h tends to 0, right, then I have sine h upon h, sine h upon h. You're taking this limit as h tends to 0. This is going to be equal to 1, right? So this is going to be 0. This is going to be 1. Now, these are the few ones we are going to be dealing with as time goes on. So we're going to be using this concept to solve for exponential x over here. So let me use this portion of the screen, and let's solve for this guy over here. Now, remember, we want to differentiate this guy using the first principle. So this is going to be the limit as what? As h tends to 0 of exponential, instead of x, it's going to be a step further. So I have x plus what? Plus h minus what? Exponential x upon h. Fantastic. So you remember from our indices, this is the same thing as the limit as h tends to 0 of exponential x and exponential h. Is that not so? This is how I'm going to represent this guy, because we have positive here and from a normal index. So we have minus exponential x. This is upon what? Upon h. So here I'm going to have the limit as x, as changing x, which is now h, since we're using the definition h. H tends to 0. So here I can factor out exponential x into, we have exponential h minus, what is going to be here? Minus 1, right? Minus 1, because we have exponential h over here, exponential x, which we have factored out. So we're left with 1 over here upon what? Upon h, right? So I can decide to take the limit here. If I take the limit here, everything over here is going to be going toward 1, because of this identity that we have, this standard limit that we have over here. So after taking the limit, I'm going to have everything here is equal to 1. So I'm going to have exponential x multiplied by 1. So this is why you have exponential x. So remember, when you differentiate exponential x, you're going to get exponential x. So you see, that is the reason. So basically, this is a very fantastic example. So over here, what are we going to be doing again? Now, let's try and get what is sine x, right? So let me take away everything that's on the board. You can always keep the video to this point. If you want to understand more, you can always rewind this video, and then you can save this video, right? Please remember to subscribe to our channel so that we can grow, and this video will be recommended to so many other people on YouTube. Now, let me take away everything and try to solve this particular sine x, right? So what we'll have here is f of x is equal to sine x. So remember, our first derivative, just know, is very simple. You don't need to memorize this. As h tends to 0, the function evaluated at a step further minus your function f of x, then upon h. H is changing x, right? So what do you have there? Over here, you can say, if I want to evaluate that function, I have f of x Then I have the limit as h tends to 0. Then I have sine, instead of x, I will have x plus h. Fantastic. Then minus sine x upon what? Upon, what do we have? Upon h. Now, this is very simple because what do we know? We know from our trigonometric ratio, from the trig identity, that sine x over here is going to be sine x, right? Multiplied by cos h, which is the second one. Then we have plus cos what? Cos x. Then we have sine h, right? This particular guy is going to give us everything over here. So we have minus sine x, right? So this all is upon what? Upon h. So over here, we can now take out this element. Correspondingly, we have sine x over here. We have another sine x over here. So let's bring them together. So we have sine x cos h. Then we have minus sine x minus sine x. So here we have positive cos x, and then here we have sine h, right? So this is all over what? Over h, right? So technically, we can now try to factor out sine x here, over here. If you factor out this sine x over here, you are left with what? You are left with, so sine x can be outside. Then I'm going to factor cos h minus, whoa, what are we going to have here? I've taken sine x outside, so I'm going to get 1, right? Because I factor out sine x outside. So if I multiply this, I'm supposed to get this back. So sine x multiplied by cos h is this. Sine x multiplied by minus 1, negative 1 is this. So I have here plus cos x sine h. Now, all this is all over h. Now, since the denominator is the same, I can decide to split them out, right? So I can decide to have something like the limit as h tends to 0. So here I'm going to have sine x cos h minus 1. Now, this can be all over h, right? And then I can have this side separated. I can have cos x sine, what do you call it? H upon, then this guy is going to be what? H, right? So all these elements are the same. The denominator, since the denominator is for all of them, I can decide to split them this way. Now, I can take the limit here because I know from our standard limit, right? You recall that the limit as h tends to 0 of sine h upon h, this is equal to 1. So I'm going to take the limit here, and then similarly cos h minus 1 over h. If I should take this limit as h tends to 0, I'm going to get 0 over here. So if I take this limit here, right, this guy is going to be sine x multiplied by what? 0. This guy is 0. Plus, here I'm going to get cos x here, right? While this guy is going to be 1. So this is multiplied by 1. So eventually, my f prime of x is going to be what? Cos x. Fantastic. So similarly, you can do this for f of x is equal to cos x tan x and what have you, which we are going to be doing in the next video. So if you have gotten something interesting in this video, please, you can leave a like, comment, and try to share this video to as many as you can. So I will be seeing you in the next video, and thanks for watching.